Okay, so far we looked at, the general purpose register, the special registers, system register, this and that. And now I want to take a moment and guide on, or explore how this A-class CPUs boot up, right? And this kind of, should enable you to imagine end-to-end flow of what goes on. Firstly, again, let me get myself out of the way, and I'm not looking as awesome, so I'll turn the lights on. Okay, so this is nice. Okay, so what I want to do now is want us to imagine and imagine with better colors that this is a CPU, which is the A-class CPU, right? And we are talking about, we're going to explore how this boots up. So the moment power is released on this thing, right? The reset is released, so to speak. What will happen is the program counter will be pointing to a memory, a location in the memory, and that's like hard coded in that program counter. Again, there are mechanisms as to how that can be changed and this and that, but safe to assume that this CPU, as it starts, the power is turned on it, the program counter is pointing to some memory location, and whatever is the instruction at that point, it will simply start to execute it, right? It will just start to fetch one instruction after the other, and go ahead and execute. Now, usually what happens is we start off with some assembly code, and that assembly code eventually may kind of jumps into the or jumps to the location where the code generated as a result of the C files is present. Essentially, you wrote code in C, and that is what now we want to, execute the assembly or the machine code generated as a result. But one of the things about C function calls, right, uh, is that it requires stack, right? And typically each processor provides like a register to be treated like a stack pointer, and so we have like a stack pointer dedicated within the A-class CPUs. And so your initial code here, some part of the code here needs to set, load the stack pointer with a valid memory address, so that once the execution jumps to code that requires the stack is available, right? The stack pointer is pointing to the right location. So these are like the two preconditions. The program counter is going to point to a memory location and start to execute from there. But if you have your code, which was, as a result of the C language and function calls are involved, then you must also set the stack pointer. All right. And this is key because as we explore in our case study, we'll take a look at the fact that, the stack pointer was loaded. All right. This is now like, single core boot. Now let's take a look at what happens in case of, multi-core boot, right? So you have A-class CPUs of the same type or capable or same architecture, let's say, right? And this situation is called SMP, simultaneous multiprocessing. So what will happen is each of their program counter will point to the exact same memory location, right? And now the thing is, each one of them is going to fetch exactly the same instructions and do the processing. But now obviously we have four CPUs, so something we should take advantage of their parallel execution capabilities. So then what you want to do is somehow make CPU, let's say CPU 2 jump elsewhere, CPU 3 jump elsewhere, and CPU 4 jump elsewhere, where you have different code, and so that they can go ahead and execute some other program like a actual in parallel, right? Execute as an independent entity. So the question is, how do we do that? And then the second thing is, if this code now was a result of the C code, like generated from C code, and functional calls were involved, then each of the CPU, the stack pointer within, right? The stack pointer should also point to different locations in RAM, so that the stacks are separate. Because if we don't do it and only set like the same stack pointer on all of them, the different codes are going to kind of, screw up each other's stack, essentially use the same memory location as the stack, and that is not good. So we, on multiprocessing systems, then we want the program counters to eventually diverge, go to different places. And we also want the stack pointers to be set differently, right, for each processor. So the question was then, how can you make each processor jump to different code? And the answer to that is that there is a register called MPIDR on each of these CPUs. It's CPU specific. So what can we do is, as they start off, with this pointing to the same memory location, in the initial as part of the initial code, what we can do is read this MPIDR register and infer the ID of the CPU, right? And then based on which CPU it is, we can go ahead and load the stack pointer with different addresses, and those addresses are to depend on some mathematics relating to the ID. A good example would be, let's say we say that the stack pointer can start at the memory location, let's say hex 1000, for example. Now, if the ID of the CPU is, let's say, for example, 0 in primary core, then we can say, hey, ID into 1000 plus 1000, like hex 1000, right? And this 1000 is essentially this, right? And we can say, okay, load the SP with this value. Now, what will happen is, for the ID 0, we'll point CPU 0 at hex 1000, but CPU 1 now will point to hex 2000, right? So essentially, we are separating each of their stack by, hex 1000, which is 4K, and then the mathematics is dependent on the ID. So that is one clever trick in which we can set different stack pointers for different CPU based on its ID, right? And so I think this register is MPIDREL1, if I'm not wrong. And then the other thing is, similarly, we can use the ID to kind of also, make the individual CPU jump to different locations. Right? And if we achieve that, then we have each of the processor with its own stack pointer and pointing to different memory location to fetch the instructions, and off they go in their different directions, and execute different programs. Now, setting up all of this is obviously more involved, and there are many more settings to get the CPU to be set up properly and actually boot up to the operating system. But this is the bare minimum. You need the program counter to be or rather, your code needs to be at the location where the program counter will point to. And the second thing is, the stack pointer needs to be set. And if you're going after multi-core, then you have to cleverly use the MPIDR register to send each of the core to different locations to fetch the instructions from. All right. So that is about how the CPUs boot up. In the next video, we'll dive into a use case or a demo which kind of guides on the multi-core boot.